In the vastness of the cosmos, power is everywhere, but not the kind of power we understand on Earth. Out there, forces exist that can rip apart stars, bend space itself, and unleash more energy in a few seconds than our sun will emit in its entire 10 billion year lifetime. They are so extreme that even our most advanced theories struggle to explain them, and yet without them, the universe as we know it could not exist. These are not gentle processes. They are explosions that can outshine entire galaxies, black holes that devour light itself, and invisible forces that quietly stretch the universe apart. For a brief moment in time, some of these events release more energy than all the stars in the cosmos combined, sending shockwaves across space-time and rewriting the fate of everything nearby. And yet, here's the paradox. These same destructive powers are also the architects of creation. They forged the atoms in our bodies, lit the first stars, and continue to shape galaxies across billions of light years. Without them, there would be no planets, no life, and no one to look up at the night sky and wonder how it all began. Tonight, we're going on a journey through the most extreme forces in existence. From the hidden wars inside every atom, to the titans that dominate the hearts of galaxies, from the silent pull of dark energy to the speculative edges of the multiverse itself, these are the powers that define the universe, forces so overwhelming they blur the line between creation and destruction. And it all begins not in the distant galaxies, but deep inside the smallest building blocks of matter, where an invisible battle rages, and the strongest force in the universe holds everything together. Deep inside every atom, in the heart of every proton and neutron, an invisible war is raging. Protons are crammed together in the nucleus, all of them carrying positive charges that should repel each other with overwhelming force. By all logic, they should fly apart instantly. And yet they don't. They stay locked in place, bound so tightly that the very fabric of matter holds together. The reason is the strongest force in the universe, the strong nuclear force. Unlike gravity, which pulls across infinite distances, or electromagnetism, which stretches from one end of the cosmos to the other, the strong force works only at impossibly small scales, fractions of a femtometer, less than the width of a single proton. But within that tiny range, it is absolute. Scientists measure it as 100 times stronger than electromagnetism and trillions upon trillions of times stronger than gravity. If gravity is a whisper, the strong force is a thunderclap that shapes the entire universe. The carriers of this force are particles called gluons, aptly named because they act like chains binding quarks together. Inside each proton and neutron, 3 quarks are trapped in a prison of pure energy, held together by a web so complex that even the most powerful supercomputers struggle to model it. And here's where the strangeness begins. The more you try to pull quarks apart, the stronger the force becomes. It's like stretching a rubber band that grows thicker and tougher the further it's pulled. No matter how much energy you apply, you can never isolate a single quark. Instead, the energy you put in just creates more quarks and gluons, new links in a chain that can never be broken. This bizarre behavior, known as confinement, is what makes stable matter possible. It decides which atomic nuclei can exist, sets the rules for nuclear fusion in stars, and determines how elements are forged in the crucibles of stellar cores. Without it, protons would fly apart, stars would never ignite, and the universe would be nothing but a thin fog of particles drifting forever in the dark. But even this force, supreme as it is, has its limits. It holds sway only inside the nucleus. Step beyond that microscopic realm, and other powers begin to dominate. And when they do, the results can be violent beyond imagination. Somewhere in the depths of space, a single dying star prepares to unleash an explosion that will outshine entire galaxies. Somewhere in the universe, a star far larger than our sun is coming to the end of its life. For millions of years, it has burned with unimaginable intensity, consuming its fuel at a rate so extreme it was destined to live fast and die young. Now, in its final moments, its core collapses under the crushing weight of gravity, and what follows is the most violent explosion the cosmos can create: a gamma-ray burst. For a few short seconds, a gamma-ray burst releases more energy than our sun will produce over its entire 10 billion-year lifetime. Jets of matter and radiation are fired from the dying star's poles at nearly the speed of light, piercing through the collapsing layers like bullets tearing through tissue. When they break free, they unleash beams of energy so focused and powerful they can travel across billions of light years without scattering. If your eyes could see in gamma rays, these blasts would appear brighter than the full moon, flashes of light brighter than entire galaxies, yet lasting less than a heartbeat. These explosions don't just dazzle, they shape the universe. Gamma-ray bursts are thought to seed space with heavy elements, scattering the building blocks of planets and life. Their power is so immense that if one erupted within our own galaxy and pointed directly at Earth, it could strip away our atmosphere in seconds. Thankfully, the cosmos is vast, and these titans usually roar from distant galaxies, their light carrying messages from the early universe itself. In October 2022, astronomers detected the most powerful burst ever recorded, nicknamed the Boat, the brightest of all time. It was so intense that it overloaded detectors across the solar system and even disturbed Earth's upper atmosphere, despite erupting from a star more than 2 billion light-years away. For a brief moment, a single star outshone every other source of light in the sky. Yet, as ferocious as they are, gamma-ray bursts are only one piece of the story, because when the dying core of a massive star collapses, it doesn't just explode, it often leaves behind something even stranger, a black hole. And some of these black holes grow to scales that defy belief, swallowing entire star systems and reshaping galaxies around them. At the heart of almost every galaxy lurks a monster, black holes, so massive they make ordinary stars look insignificant. These are supermassive black holes, cosmic giants weighing millions, even billions of times more than our sun. Yet squeezed into a space smaller than our solar system, their gravity is so overwhelming that not even light can escape once it crosses the event horizon. To the outside universe, they appear as bottomless pits in space-time, silent voids that consume everything unlucky enough to drift too close. But these monsters are not always quiet. When gas, dust, or even entire stars fall toward them, they form a swirling disk of matter heated to millions of degrees. This accretion disk glows so brightly it can outshine every star in the galaxy combined. In some cases, magnetic fields twist and funnel material into colossal jets that blast out from the black hole's poles at nearly the speed of light. These beams stretch for hundreds of thousands of light-years, carving through space with surgical precision, reshaping galaxies and preventing new stars from forming. A single black hole in its hunger can control the fate of an entire galaxy. What makes these giants even more mysterious is how quickly they appear. We see quasars, galaxies lit by feeding black holes, shining from less than 1 billion years after the Big Bang, meaning some black holes grew to billions of solar masses in what amounts to a cosmic instant. How they manage this impossible growth remains one of astronomy's greatest puzzles. And yet, even these titans are not the largest force at work in the cosmos. Because while black holes devour matter locally, on the grandest scales, something far more subtle is reshaping everything we see. An invisible energy, filling all of space, is pushing galaxies apart faster and faster, rewriting the universe's ultimate fate. Across the universe, Galaxies are drifting away from one another, carried by the expansion of space itself. For decades, scientists assumed that gravity would eventually slow this expansion down, maybe even reverse it in a grand collapse. But when astronomers studied distant supernovae in the 1990s, they found something no one expected. The expansion isn't slowing at all, it's speeding up. Some unseen force is pushing the universe apart, stretching the very fabric of space-time. We call it dark energy, and it makes up nearly 70% of everything that exists. Unlike gravity or electromagnetism, dark energy doesn't weaken with distance. In fact, the more space there is, the stronger its influence becomes. As the universe grows, more dark energy fills the void, accelerating expansion even further. It's like a cosmic gas pedal that only knows one direction, faster and faster forever. The galaxies aren't flying through space like rockets. Instead, space itself is expanding between them, carrying them away from each other like boats drifting apart on a swelling ocean. For now, the effect is gentle. Galaxies remain bound together in clusters, stars still orbit within galaxies, and planets cling to their suns. But if dark energy continues its relentless growth, the distant future looks terrifying. Over billions of years, galaxies will vanish beyond the cosmic horizon, unreachable and invisible. Later still, stars within galaxies could drift apart, solar systems could unravel, and in some scenarios, even atoms themselves might be torn to pieces in a final catastrophe known as the Big Rip. And yet, without dark energy, the universe would look nothing like it does today. It is the quiet architect of cosmic structure, shaping the vast web of galaxies, while steering the ultimate fate of reality itself. But while dark energy works on the largest scales imaginable, the universe also hides extremes on the smallest scales, remnants of dead stars that compress matter into states stranger than anything we can create on Earth. And some of them, with magnetic fields beyond comprehension, can unleash power that rivals entire galaxies. When a massive star dies, but isn't quite heavy enough to collapse into a black hole, it leaves behind something almost as terrifying, a neutron star. Imagine cramming the mass of our sun into a sphere barely 20 kilometers across, smaller than a city. The result is matter so dense that a single teaspoon would weigh billions of tons. Gravity on the surface is crushing beyond imagination. Drop a marshmallow from waist height and it would strike with the energy of a nuclear bomb. But density is only part of the story. Neutron stars are also magnetic monsters. Some, called magneteers, possess magnetic fields a trillion times stronger than Earth's. These fields are so powerful they can twist atoms into needle-like shapes, erase every credit card on Earth from halfway to the moon, and trap particles in beams of radiation that sweep across space like cosmic lighthouses. When a magneteer's crust cracks under the strain of its own magnetic force, the resulting starquake can release more energy in 1/10 of a second than our sun produces in 100,000 years. From thousands of light years away, these eruptions can disrupt Earth's atmosphere. On their spinning axes, many neutron stars fire beams of radio waves or X-rays with clock-like precision. We call them pulsars, and some spin hundreds of times per second, more stable in their timing than any human-made atomic clock. Each pulse is the heartbeat of a dead star, echoing across the galaxy. Yet even these stellar corpses are not the strangest relics of the cosmos. Beyond them, theorists imagine objects far more exotic, threads of pure energy stretched across the universe since its birth, so thin they make a proton look enormous, yet so heavy they could outweigh a planet. If they exist, they are scars from the first moments after the Big Bang, and their power would be unlike anything we've ever known. In the earliest moments after the Big Bang, when the universe was hotter and denser than anything we can recreate, space itself may have fractured. As it cooled and expanded, cracks could have formed in the very fabric of reality. Cosmic strings. These are not strings like in a violin or rope, but one-dimensional objects thinner than a proton, yet so heavy that a single kilometer of string would outweigh Earth. They are remnants of ancient phase transitions, scars left over from the universe's birth, stretched across space like invisible threads of unimaginable energy. If cosmic strings exist, they would be the ultimate expression of density and tension. Moving through space, they could slice through planets, as if they were nothing more than mist, leaving behind shockwaves in spacetime itself. When two strings cross, they might snap and reconnect, forming loops that vibrate like plucked guitar strings. But instead of sound, they radiate pure gravitational waves, rippling outward across the universe. A single loop could release enough energy to dwarf the output of every star in the galaxy. Some theories even suggest cosmic strings could act as shortcuts through space, natural highways across the cosmos. In higher dimensional models, they might be fragments of hidden realms intersecting with our universe, windows into dimensions we cannot perceive. To detect one would be to glimpse the handwriting of the cosmos itself, a relic of the universe's first heartbeat. So far, they remain theoretical, hiding in equations and speculation, their presence hinted at only through indirect clues. But if we ever confirm them, cosmic strings would rank among the most powerful and exotic structures in existence. And yet, even without them, we already see evidence of titanic forces unleashed by known objects. Forces that carve across galaxies, launching rivers of energy so vast they outshine entire star systems. At the centers of some galaxies, black holes do more than consume. They create some of the most spectacular displays in the universe. As matter falls toward a supermassive black hole, it forms a swirling accretion disk hotter than the cores of stars. Twisting magnetic fields catch some of that material and hurl it outward in narrow beams called quasar jets. These streams of plasma travel at 99.9% the speed of light, focused so precisely they remain straight for millions of light years. To grasp their scale, imagine a jet extending far beyond the size of the galaxy that launched it. Threads of light and matter piercing the intergalactic medium. If one were aimed directly at Earth, it would appear brighter than every other star in the night sky, a lighthouse from billions of light years away. These jets are so powerful they can reshape galaxies themselves, heating surrounding gas to millions of degrees and halting star formation across entire regions of space. A single quasar jet can carry more energy than 1 trillion stars combined, sustained for millions of years. Even more astonishing, when turbulence twists through these jets, they flare with bursts of light that can brighten and fade within days, despite stretching across distances larger than galaxies. To observers on Earth, the moving knots within them can even appear to exceed the speed of light, a trick of perspective created by their incredible velocities. Quasars remind us that black holes are not merely cosmic vacuum cleaners. They are engines, tapping into gravity itself to release energies greater than any other known process in nature. Yet even these titanic beams are not the universe's final word on destruction and creation. Because sometimes the most unassuming stars, the ones that should be long dead and quiet, become the triggers of some of the most precise and violent explosions ever observed. Far out in the galaxy, a white dwarf star, what's left after a sun-like star dies, quietly orbits its companion. At first glance, it looks harmless, a cooling ember the size of Earth, but with the mass of the sun. But white dwarfs have a dangerous secret. If they draw in too much material from a nearby star, their calm exterior turns into a ticking bomb. As hydrogen piles onto the white dwarf surface, it's squeezed under gravity until the pressure and temperature soar high enough to ignite nuclear fusion. The star becomes a cosmic pressure cooker, holding back a reaction it cannot sustain. Once the white dwarf reaches about 1.4 times the mass of the Sun, a threshold known as the Chandrasekhar limit, stability ends in an instant. The entire star detonates in a Type 1a supernova. Unlike other stellar explosions, this one leaves nothing behind. The white dwarf is obliterated completely, releasing a flash so bright it outshines entire galaxies. For weeks, the supernova burns with the light of billions of suns before fading back into darkness. These explosions are so consistent in brightness that astronomers use them as cosmic mile markers, measuring the scale of the universe itself. But their importance goes even deeper. Type Ia supernovae are factories of the elements that make us who we are. The calcium in your bones, the iron in your blood, the nickel in coins, all forged in these thermonuclear blasts and scattered into space to seed new generations of stars and planets. Without them, life as we know it could never have formed. And yet, as violent as these explosions are, there are stellar deaths even more extreme. When two neutron stars, the densest objects in existence, spiral together in a final dance of doom, the collision shakes the universe itself, forging treasures more precious than anything found on Earth. Two neutron stars, each heavier than the Sun, but barely the size of a city, spiral around one another in a deadly embrace. For millions of years, they orbit closer and closer, their immense gravity distorting each other's shapes and sending ripples of energy through space-time. These ripples are gravitational waves, stretching and squeezing the fabric of reality itself as they race outward at the speed of light. With every orbit, the stars lose energy, spiraling faster, tighter, and hotter until the final seconds arrive. In that last instant, the neutron stars whip around each other hundreds of times per second, moving so fast they blur space itself, and then they collide. The impact is unlike anything else in the universe. A kilonova, an explosion that releases both a flash of gamma rays and a fireball of radioactive material glowing brighter than entire galaxies. For weeks, the wreckage shines, fading slowly as newly forged elements decay into stability. Inside this chaos, nature performs its most precious alchemy. The extreme conditions bombard atomic nuclei with neutrons, so rapidly that they build elements heavier than iron, elements that normal stars cannot create: gold, platinum, uranium, all born in the instant when neutron stars smash together and then hurled across space at a third of the speed of light. A single merger can create more gold than exists in our entire solar system. These collisions don't just enrich the cosmos, they confirm predictions made a century ago. In 2017, scientists detected both gravitational waves and light from a single neutron star merger for the first time, proving that these events are among the universe's most powerful forges. But as violent as they are, neutron star collisions are still only one chapter in a much bigger story. To truly understand where all power begins, we must rewind the clock, not millions or billions of years, but all the way back to the very first fraction of a second, when everything we see today was compressed into something smaller than a particle. 13.8 billion years ago, everything that exists, every galaxy, every star, every atom in your body, was compressed into a point smaller than a proton. This was the singularity, the moment before time and space, as we know them, existed. Then, in less than a heartbeat, it all changed. The universe didn't explode into empty space. Space itself expanded, dragging matter and energy outward in every direction. This was the Big Bang, and it was the most powerful event in history. But what happened next was even stranger. In the first split second, the universe underwent a period of inflation, expanding faster than the speed of light. In less time than it takes light to cross an atom, space stretched by factors of billions upon billions. Regions that were once impossibly small were blown up to cosmic scales, ironing out irregularities and planting the seeds for the galaxies that would one day form. Tiny quantum fluctuations, random jitters in energy at the smallest scales, were stretched across the cosmos, becoming the patterns of density that gravity would sculpt into stars and galaxies. In other words, everything we see today, from spiral galaxies to the Milky Way itself, was born from microscopic fluctuations in the first instant of time. As the universe cooled, the fundamental forces began to separate. Gravity split off first, followed by the strong nuclear force, and then electromagnetism and the weak force. Matter began to stabilize, protons and neutrons formed, and within minutes, the first atomic nuclei were forged. For hundreds of thousands of years, the cosmos was a glowing fog, until atoms finally took shape and light was free to travel across space. That ancient glow still surrounds us today as the cosmic microwave background, the faint afterglow of creation itself. And yet, even this origin may not have been the ultimate beginning. Some theories suggest inflation never truly ends, creating bubble universes over and over in an endless process called eternal inflation. If that's true, our Big Bang was not unique. It was simply one bubble among countless others, each with its own physics, its own history, and its own fate. But if our universe was just one bubble, what other forms of cosmic death and rebirth might be waiting? In the lives of massive stars, there are explosions so powerful they make even supernovae look tame, hypernovae, stellar deaths that push nature to its breaking point. When an ordinary massive star dies, it ends in a supernova. But for the most massive, fastest spinning stars in the cosmos, death comes in an even more violent form, a hypernova. These rare explosions release 10 to 100 times more energy than a typical supernova, making them some of the most extreme events the universe can produce. A hypernova begins when a star more than 30 times the mass of the Sun burns through its nuclear fuel. With nothing left to counteract gravity, its core collapses almost instantly, forming a newborn black hole. But unlike ordinary collapses, the star's rapid spin and intense magnetic fields create a cosmic dynamo, amplifying the chaos to unimaginable levels. Twisted magnetic fields act like springs wound to their breaking point, snapping and channeling material into jets of matter and radiation blasting outward at nearly the speed of light. These jets punch through the dying star, tearing it apart from the inside. The result is a gamma-ray burst, one of the brightest signals we can detect across billions of light-years. The energy released in seconds dwarfs what our sun will produce over its entire lifetime. Deep inside the collapsing star, layers of carbon, neon, silicon, and iron ignite in a cascade of nuclear reactions, forging heavy elements in mere seconds before hurling them into space. Hypernovae are rare, but their influence is immense. They enrich galaxies with elements like nickel, cobalt, and titanium, scattering the raw ingredients for future planets and life. Their shockwaves compress nearby gas clouds, triggering new waves of star formation, while also sterilizing vast regions of space with radiation. They are both creators and destroyers on a galactic scale. And as violent as hypernovae are, they aren't the only exotic pathways to cosmic power. The universe may hide energies even stranger, released not by stars at all, but by invisible matter that outweighs everything we see, silently shaping galaxies and perhaps capable of annihilating itself in bursts of pure energy. All around us, an invisible substance outweighs every star, planet, and cloud of gas in the universe 5 to 1. We call it dark matter, and though we can't see it, its gravity sculpts galaxies, binds clusters together, and holds the cosmic web in place. Without it, the stars would never have gathered into spirals or formed galaxies at all. But dark matter doesn't interact with light or ordinary matter in any way we can directly detect, which makes it one of the greatest mysteries in physics. Some theories suggest that dark matter may be its own antiparticle, meaning that when two dark matter particles meet, they annihilate completely, converting all of their mass into energy. If this is true, then hidden across the universe are invisible fireworks, bursts of radiation powerful enough to rival the combined output of entire galaxies. In the dense cores of galaxy clusters or in the crowded regions around black holes, these annihilation events could be happening constantly, creating showers of high-energy particles and gamma rays. Astronomers have even searched for such signals, hoping to catch the faint glow of dark matter destruction. A confirmed detection would not only reveal what dark matter truly is, but also prove that some of the most violent energy sources in the cosmos come from matter we cannot even see. Imagine a single kilogram of dark matter releasing as much energy as millions of tons of explosives, silent, invisible, and unstoppable. So far, the evidence is tantalizing, but not conclusive. The annihilation glow remains hidden, leaving us with only the pull of gravity as proof that dark matter exists at all. But if dark matter can self-destruct, then it might also hold the key to understanding the fate of galaxies themselves. And dark matter isn't the only ancient remnant shaping the cosmos. From the first second of existence, there may be even stranger relics still out there. Tiny black holes born at the dawn of time, each one carrying the weight of mountains inside something smaller than an atom. In the chaos of the universe's first moments, when everything was compressed into a fireball smaller than an atom, tiny fluctuations in density could have created some of the strangest objects imaginable, primordial black holes. Unlike the black holes we know, which form when massive stars collapse, these ancient relics could have been born less than a second after the Big Bang, with sizes and masses that defy normal rules. Some might be no larger than an atom, yet weigh as much as a mountain. Others could rival stars, lurking invisibly in the darkness between galaxies. What makes them so extraordinary is their scale. A primordial black hole with the mass of a mountain would be smaller than a proton, yet its gravity would be strong enough to warp space and time on an atomic level. The tiniest ones, according to Stephen Hawking's predictions, wouldn't last forever. Black holes slowly evaporate by releasing what's called Hawking radiation, and as they shrink, the process accelerates. In their final moments, they would unleash a burst of energy equivalent to millions of nuclear bombs in the blink of an eye. If any of these small primordial black holes still survive, they could be ticking cosmic time bombs, waiting to explode in flashes of pure energy. Larger primordial black holes might still be roaming the universe today, invisible but detectable through their gravitational effects. Some scientists even propose that these ancient black holes could make up a significant portion of dark matter, hiding in plain sight as the unseen scaffolding of galaxies, and the most massive among them may have served as seeds for the supermassive black holes we now find at the centers of galaxies, explaining how those cosmic giants grew so quickly in the early universe. If primordial black holes exist, they are windows into the very birth of reality. Objects formed before stars, before galaxies, before even atoms themselves. But the story doesn't end there, because even the empty spaces between stars and black holes, the void we call nothingness, may not be empty at all. On the smallest scales, the vacuum itself is alive with energy, and it may be the most powerful force of all. What we call empty space is anything but empty. Even in the deepest voids, stripped of matter and cooled to absolute zero, the vacuum itself seethes with activity, Particles flicker into existence and vanish again in time so short they can never be observed directly. This restless background is known as quantum vacuum energy, and it may hold more power than every star and galaxy combined. According to quantum mechanics, uncertainty rules everything, even nothing. Virtual particles constantly borrow energy from the vacuum, exist for a fleeting instant, and then disappear, paying back what they borrowed. But their presence has real measurable effects. Two metal plates placed close together are pushed toward each other by this hidden pressure in what's called the Casimir effect, proof that the vacuum is alive with invisible force. Near black holes, these fluctuations can become real, creating Hawking radiation that slowly causes black holes to evaporate into nothingness. In the earliest moments of the universe, these quantum jitters were magnified to cosmic scales. Inflation stretched tiny fluctuations into vast ripples, seeding the galaxies, stars, and planets we see today. Every structure in the universe, every cluster of galaxies, every spiral arm, even the ground beneath your feet, traces back to microscopic vibrations in the vacuum of space. When the cosmos was smaller than an atom, the numbers are staggering. Calculation suggests that the energy density of the vacuum should be 10^420 times greater than what we actually observe. An absurd mismatch known as the cosmological constant problem. If the equations were right, the vacuum would be so unstable that atoms could not exist, and the universe itself would have torn apart instantly. Yet here we are, in a cosmos that somehow balances on the edge of this paradox, stable enough for life yet humming with invisible energy. Some theories even propose that our entire universe may have sprung from a quantum fluctuation, a spark from nothing that became everything. If that's true, then emptiness is the ultimate creator, and reality itself is a product of the vacuum's restless energy. And if the vacuum can spawn one universe, why not many? Beyond our cosmic horizon, there may be countless others, bubbles of reality expanding endlessly, each with its own laws, each born from the same quantum sea. Beyond the edge of everything we can see, past the farthest galaxies and the faintest whispers of light, lies a possibility more staggering than any single explosion or black hole. What if our universe is not the only one? What if the Big Bang that created our cosmos was just one of countless others, bubbling into existence from an infinite sea of creation? This is the idea of the multiverse, and if it's true, then our universe is only a single bubble in an endless ocean of realities. In one version, eternal inflation never stops. While our patch of space cooled and formed galaxies, other regions kept expanding, each spawning its own bubble universe. These bubbles can have completely different physical laws. Gravity might be stronger, atoms might not exist, stars might never form. In others, conditions could be so alien that even the concept of matter as we know it has no meaning. Our universe, with its delicate balance that allows life, could be just one of infinite variations. Another vision comes from quantum mechanics, where every possible outcome of every quantum event spins off into its own universe. In this view, each choice, each fluctuation creates a new branch of reality. Right now, there may be versions of you living completely different lives in worlds that split from ours long ago. The implications are staggering. If the multiverse exists, then all possibilities are realized somewhere. There could be universes where stars never ignite, and others where black holes dominate everything. Some may collapse back into nothing within seconds of their birth, while others expand forever, birthing galaxies beyond counting. And perhaps the strangest thought of all, the reason we find ourselves here, in this particular universe, may simply be because it's one of the few where conscious observers can exist at all. Out of infinite possibilities, we live in the rare bubble where the conditions align just right for life to ask the question, why is there something instead of nothing? But the multiverse doesn't end the mystery. It only deepens it. Because if infinite universes exist, then where did the multiverse itself come from? Is there an ultimate origin beyond even this endless sea of creation? Or does reality have no beginning and no end? The universe, it seems, is not just stranger than we imagine, it is stranger than we can imagine. From the smallest scales inside an atom to the vast horizons beyond our universe, one truth becomes clear: the cosmos is driven by forces that are both terrifying and beautiful. The strong nuclear force locks quarks together, shaping the matter that makes us. Gamma-ray bursts blaze across galaxies, turning the deaths of stars into beacons brighter than entire universes. Black holes grow into giants that bend time and hurl jets across millions of light years. Dark energy silently stretches space itself, steering everything toward an unknown fate. Neutron stars and magnetas crush matter into impossible states, while hypernovae, kilonovae, and white dwarf detonations forge the very elements that built our world. Even in the void, the quantum vacuum teems with energy, hinting that reality itself may have sprung from nothing. And beyond all of it, the multiverse suggests that our universe might be only one page in an infinite book of creation. What's most astonishing is that these forces don't just destroy, they create. They sculpt galaxies, ignite stars, and seed the ingredients for life. They shaped Earth, and they shaped us. The calcium in our bones, the iron in our blood, the gold in our rings, each was forged in cosmic violence billions of years before humans ever walked the Earth. We are not separate from the universe's power, we are its direct expression. Perhaps that is the greatest force of all. Not destruction, not expansion, not even the ability to create stars, but the universe's capacity to give rise to awareness, to produce beings who can look back across time, trace their origins to the heart of dying stars, and wonder what it all means. In that sense, the universe has done something more profound than unleash explosions or bend spacetime. It has learned to know itself through us. So, the next time you look up at the night sky, remember, you are stardust, assembled by forces older and stronger than you can imagine. You are part of a story still unfolding, a universe awakening to its own existence. And perhaps the most powerful truth of all is this: the cosmos isn't just out there, it is within you, written into every atom, every thought, every heartbeat,